In the summer of 1997, an array of hydrophones anchored to the floor of the South Pacific recorded a sound. It lasted roughly 1 minute. It rose rapidly in frequency. It was loud enough to be picked up by sensors more than 5,000 kilometers apart. The National Oceanic and Atmospheric Administration catalogued it, assigned it a name, and moved on. They called it Bloop. For the next 6 years, Bloop existed as a footnote in an oceanographic database. Then the internet found it, and within a decade, it became the most famous unidentified sound in the ocean. The spectrogram was everywhere: forums, documentaries, Reddit threads. The theories ranged from undiscovered megafauna to geological events to classified military experiments. A marine biologist at Oregon State, Christopher Fox, said something careful in an interview. The sound profile was consistent with a biological source, but the amplitude exceeded any known animal. That sentence did more work than he intended. It became the seed of a mythology. An animal too large for science. Something in the deep Pacific making a sound louder than a blue whale. But the sound was not the mystery. The microphones were. During the Cold War, the United States Navy installed a network of hydrophones across the ocean floor. The system was called SOSUS, Sound Surveillance System. Its purpose was to detect Soviet submarines by listening for the acoustic signatures of their engines and propellers. The hydrophones sat at a very specific depth, roughly 700 to 1,200 meters below the surface. Not randomly. At that depth, a combination of temperature, salinity, and pressure creates a layer where the speed of sound reaches its minimum. Sound waves that enter this layer do not escape. They bend inward, refracted back toward the center every time they try to rise or sink. A sound wave trapped in this channel can travel thousands of kilometers without losing significant energy. A whale calling off the coast of Puerto Rico can be heard on a hydrophone near Bermuda. A submarine running its engines near Murmansk can be detected off the coast of Iceland. This layer is called the SOFAR channel, sound fixing and ranging. It was discovered in the 1940s. It was classified almost immediately. For 40 years, it was the backbone of Cold War submarine detection. When the Soviet Union collapsed and the acoustic data was partially declassified in the early 1990s, oceanographers suddenly had access to a global listening network they never built and could never have funded. The ocean had been recorded continuously across millions of square kilometers for decades. Nobody outside the Navy had heard any of it. The first thing they heard was not submarines, it was the ocean, whale calls, earthquake rumbles, iceberg calving events, volcanic activity on mid-ocean ridges. The slow groan of tectonic plates shifting, storms on the surface registering as low-frequency pressure waves at depth. The ocean was not silent. It had never been silent. Humans had simply never had the equipment to listen at the right depth, across the right distance, for the right duration. And then there were the sounds that did not match anything. Bloop was one, but it was not alone. In 1991, hydrophones detected a steady signal rising from about 300 Hz to roughly 4,000 Hz over several seconds, then repeating. It had been running continuously since at least the beginning of the recording period. They named it Upsweep. The source appeared to come from a volcanically active region of the Pacific floor. The signal is seasonal, peaking in spring and autumn. It has been recorded every year since 1991. No one has confirmed what produces it. In 1999, a sound appeared on the Pacific arrays that lasted roughly 15 seconds. A long, drawn-out tone that dropped in frequency like something heavy sliding to a stop. They named it Slow Down. Spectral analysis suggested ice. a large iceberg dragging along the seafloor or calving in a way that produced a low-frequency resonance. The explanation is plausible, but the sound was recorded roughly 3,500 kilometers from the nearest ice sheet. In 1999, another signal. Short-duration, narrow-band rising tone. They called it Julia. It was detected across multiple arrays simultaneously, meaning it was loud. The spectrogram looks almost vocal. The proposed explanation is iceberg grounding. The explanation is consistent with the data, but it does not close the file. The frequency pattern does not match any recorded calving event precisely. Each of these sounds has a name, a date, a spectrogram, and a proposed explanation. Most of the proposed explanations are some variant of ice, seismicity, or water interaction with the seafloor. Most are reasonable, none are confirmed. The ocean produces sounds that travel thousands of kilometers through a channel designed by physics to preserve them, and we receive them on instruments that were built to find submarines. We are listening to a world that was never meant to be heard at this resolution, and parts of it do not make sense yet. Bloop itself was reclassified in 2012. NOAA concluded the sound profile was consistent with an ice quake, the fracturing of a large iceberg. The frequency, the rise pattern, the amplitude, all consistent with Antarctic ice calving events recorded elsewhere. The case, officially, is considered explained. But the word is considered, not confirmed. The match is probabilistic, not direct. No one observed the specific event that produced Bloop. No one watched an iceberg crack and matched the resulting sound to the 1997 recording. The explanation is the best available hypothesis. Science works this way, the internet does not. What the internet latched onto was the biological angle. Christopher Fox's original observation was careful and conditional. The profile was consistent with a biological source at an amplitude that exceeded known animals. That is a statement about frequency shape, not about origin. Many sounds have profiles consistent with biology. Ice cracking can resemble whale calls on a spectrogram. Geological events can produce harmonic overtones that look organic. The human ear and the human pattern recognition system is built to hear voices in noise. We have been doing it since before we had language. The SOFAR channel simply gave us more noise to listen to. But there is one sound that does not fit the pattern of geological or ice-related events. In 1989, the Navy's hydrophone network detected a whale call at 52 Hz. Blue whales call between 10 and 39 Hz. Fin whales call around 20. This call sat above both ranges. It was structurally similar to a whale vocalization, but at a frequency no known population uses. It was tracked for over 12 years. Always alone. Always the same frequency. Always moving through the same migration patterns as baleen whales, but never appearing in the same acoustic space as any group. The researchers named it 52 Blue. Some called it the loneliest whale in the ocean. The explanation is uncertain, a hybrid between species, perhaps. A whale with an anatomical anomaly that altered its vocal range, a single individual whose call falls in a frequency band that other whales may not recognize. The sound was real. The animal was real. The tracking data shows consistent migration across the Pacific, but it was always alone in the recordings. Whether it was alone in reality is a different question. Acoustic isolation is not physical isolation. A whale calling at 52 Hz in a sea of 20 Hz calls may be surrounded by others. It simply cannot be heard by them. Or perhaps it can. We do not know enough about whale hearing to say. The narrative of the loneliest whale is cleaner than the data. The ocean we hear is larger than the ocean we see. A hydrophone at the right depth can listen to events happening on the other side of a basin. Light dies in the first 200 meters. Sound in the SOFAR channel crosses oceans. When we dropped cameras into the deep, we saw creatures. When we dropped microphones, we heard a world. Clicks, groans, pulses, sweeps. Rhythmic patterns that last hours. Low-frequency hums that last years. Some of them match known sources, some do not. At the depths where pressure distorts steel and light does not exist, sound is the only thing that travels. It bends. It follows the curve of the channel. It carries information across distances that would take a ship weeks to cross. The creatures that live in the deep Atlantic have never been photographed. Some of them have been heard. Their sounds arrive on instruments built to detect war machines traveling through a layer of water that physics shaped into a highway for acoustics, and what reaches the surface is a recording of something we cannot see, cannot name, and in some cases cannot explain. The ocean has been making sounds for longer than anything has been alive to hear them. Tectonic plates grinding, water forcing its way through basalt vents, ice shelves splitting under their own weight. These are the oldest sounds on the planet. They were here before ears existed, before nervous systems, before the first cell divided. The ocean was never quiet. We were just late. We are still late. The network that listens is a fraction of what it was during the Cold War. Funding is limited. Hydrophones are expensive to maintain at depth. Most of the ocean floor has never had a microphone within 1,000 kilometers. What we have recorded is a sample, a narrow window into an acoustic world that covers 70% of the planet. And in that narrow sample, there are sounds we named but did not explain, sounds we explained but did not confirm, and sounds we have not heard yet because no one put a microphone in the right place at the right time. Somewhere below 1,000 meters right now, something is making a sound. It is entering the SOFAR channel. It is beginning a journey that will take it across an ocean. It may reach a hydrophone. It may not. If it does, someone will look at the spectrogram, check it against the catalog, and try to find a match. If no match exists, it will get a name, a file, a proposed explanation, and a note that says unconfirmed. The ocean does not explain itself.